project, our paper was on BIOBIT. So what we have tried to do is we have tried to secure the supply chain between drug manufacturers and end consumers. So end consumers get a chance to verify that the medicine that they're using is authentic, is from the actual factory that it was made in. So the problem statement that we went ahead with was 10% of medicines in low-income countries as of today are probably fake, and they're pushed into the supply chain from people who are not supposed to be part of the supply chain. And they, as you can see, they cost a lot in even in economic terms. And the traditional tracking system is has problems that a system that was secured by blockchain wouldn't face. Then So the challenges that we faced was the medicine supply chain are very complex globally speaking, even domestically. There are very few limited real-time verification mechanisms that we could build upon or use. And there's even endpoint applications often face cybersecurity threats. So what we came up with was BioBit. This is a dual layered system. So we have a blockchain backend, and then we have a front end infrastructure, like a web page front end that's secured by a locally made machine learning model that classifies packets as dangerous or not. Only safe packets are allowed to interact with our system at all. And yeah, so uh, me- fake medicines pose a very big threat, not just because they're harmful to the company in terms of economic revenue, but also to the people who will be consuming them. So we felt that this was a very good thing to work on. What we offer through BioBit is a mechanism to verify the medicine that we're consuming or taking from the endpoint, like a medicine outlet, a store, is the actual medicine that was made. How do we do this? So there's a QR code present on the medicine that is scanned by the end consumer, which is then queried as an instruction to the Hyperledger. Hyperledger verifies with an entry that it's previously made for every medicine made by the factory. And if there's a match, we tell the end user that the medicine being scanned is safe for consumption. So these were our project goals. We wanted to ensure that every medicine being consumed by everybody is authentic, eliminate counterfeit medicine, also protect the blockchain access point, the attack vectors that were the full stack application itself, and to help ensure consumers have trust in the medicines they're taking. So as we know, the blockchain itself is pretty secure because it uses the consensus algorithm. But the way that we communicate with the blockchain, our front full stack application was still prone to threats. So we wanted to ensure that only packets that are safe, or to say are not maliciously tagged by our uh, model, that is, we use an XGBoost model and trained it on the NSL-KDD dataset that is publicly available. So we wanted to make sure that every packet that goes through passes the minimum requirement that we have our model filter out all the unnecessary packets. So this is what the pipeline kind of looks like. User requests are first. Any kind of data coming onto the backend is either classified and it's only forwarded if it meets our requirements. It then is sanitized further. We only have a password verification for this as of now, and then uh, it can form queries to the Hyperledger and then to the blockchain network eventually. So
Hi,
this is what the deployment pipeline looks like.
I can take it from here.
Yeah, sure.
Sorry, everyone, I had some audio issues in my laptop. I'll be sharing. Aditya, can you share the PPT, please? We were on real-time deployment pipeline. Right. So this is the real-time deployment pipeline for our project. So when a user request or a packet enters the system, it doesn't directly go to the blockchain. So instead, it first passes through our XGBoost-based anomaly detection model, which is sitting at the application gateway. So this model has been trained to identify malicious traffic patterns in real time. So if the packet is deemed safe, it is then forwarded to our full stack application, which then interacts with the Hyperledger Fabric, the blockchain, to complete the drug verification or update the request. So if the packet is flagged as suspicious, it is immediately logged, and it can even trigger automated security responses at the SDK level. So the key advantage here is that the blockchain never interacts directly with the unverified traffic. So we've built a proactive shield that doesn't compromise on the speed and ensures only trusted data can reach the Hyperledger Fabric. So it's a security first approach and without performance penalties. Okay, so the security layers within the machine learning technology basically includes a two-tiered security mechanism. So the first is the packet filtration layer, which is powered by the XGBoost model, which is trained on the NSL-KDD dataset. That acts as a real-time gatekeeper, you can say, and it analyzes the incoming network traffic and classifies each packet. Next comes the sanitization layer. This layer performs a deep inspection of the approved traffic. It cleanses the request of any, you can say, potentially harmful inputs, such as injected scripts or malformed data. So before it reaches the blockchain environment, it performs this inspection. So together, these two layers basically form a proactive defense system that not only detects, but it can also prevent the malicious activity. And it ensures that the interaction with the blockchain is always trusted and clean. So why did we choose XGBoost? It is because it offers high performance on tabular structured data and handles missing values and skewed classes. And it provides fast inference, which is ideal for deployment at a gateway. So coming to the model evaluation, to ensure that our anomaly detection model wasn't just fast, but also reliable, we basically evaluated its performance using multiple metrics. So the model achieved a precision of 92%, meaning that it rarely flagged normal traffic as malicious, which is critical in avoiding false alarms and basically means fewer false positives. Then it also achieved a recall of 89%, which indicates its strong ability to catch a wide range of actual threats from spoofing to DOS, which is denial of service attacks. And overall, the F1 score was 90.4%, reflecting a solid balance between precision and recall. So we validated these results using a stratified k-fold cross-validation, ensuring fair distribution of attack types across each fold. And then we analyze these outcomes using a confusion matrix to understand false positives and false negatives. So most importantly, this model isn't static. It basically it's periodically retrained with new data to adapt to emerging threat patterns, and it keeps the project's gateway resilient and up to date. So some of the future machine learning enhancements that we are looking forward to are okay. So while our current model performs well, we're actively also exploring into some more enhancements which are more intelligent and more adaptive. So we plan to integrate transformer models for better handling of sequential packet data, which could further boost the detection accuracy. And with online learning, the system can learn from new threats in real time, which eliminates the need for manual retraining. And we are also looking at federated learning, which would allow training across multiple pharmaceutical networks without exposing sensitive data. And Lastly, we aim to enable smart contract alerts where machine learning insights can automatically trigger on-chain events like blocking access or flagging suspicious entries. So coming to the blockchain part for BioBit, the reason for us choosing this technology was that traditional systems are centralized and they're more prone to tampering. But on the other hand, blockchain provides us with immutability where transactions cannot be altered. It provides us with transparency. All stakeholders can access the same data, and it also provides decentralization. That removes single point of failure in the whole system. So why was it perfect for our use case? Was because it's a perfect match for pharmaceuticals where product traceability, authenticity, and compliance are crucial. So we chose Hyperledger Fabric as the backbone of BioBit because it's purpose-built for secure and enterprise-grade applications like pharmaceutical supply chains. So as a permissioned blockchain, it ensures that only verified participants like manufacturers and regulators can join and interact with the network. And it also offers role-based access control, so each stakeholder operates clearly within the defined boundaries. And using smart contracts or chain code, we've embedded our business logic, such as the drug approval, directly onto the blockchain. So this is some key feature, and with CouchDB integration, we can perform powerful key value based queries like retrieving all patches by the drug ID or by the manufacturer. And thanks to its modular architecture, we can plug in different consensus algorithms or identify systems, making BioBit highly adaptable to future enhancements or needs. So the blockchain workflow, how the workflow summary for blockchain in our project is summarized as, so the BioBit workflow is designed to ensure end-to-end authenticity and accountability in the drug supply chain. So this begins with the manufacturer who uploads drug details and a unique QR code to the system. And this data is then sent to a regulatory authority or RA for review. The RA then validates this information and either approves or rejects the request. Once it's approved, the data is stored immutably on the Hyperledger Fabric along with a hashed version of the QR code. When the end user scans this QR code, the system rehashes it and compares it with the entries on the blockchain. So if there is a match, then the drug is verified, and if it's not, it's flagged as a potential counterfeit. So the result is a fully auditable tamper-proof record, ensuring that every drug can be trusted for all the way from its origin to the end user. So this was the workflow summary. Hyperledger Fabric is basically a permission blockchain platform, which which is a perfect use case fit for us. And unlike the public blockchains, like example here, Bitcoin, it restricts access to verified participants, offering enhanced privacy and control. So the key features for this Hyperledger Fabric and why we chose to use it are because it is a permissioned blockchain. The access is controlled via certificate authorities or CAs, and it consists of a modular architecture or pluggable components like consensus and membership, which allows us flexibility with the algorithms. The smart contracts or chain code, the business logic, which is written in Go, Java, Node.js, and it is run on peers. Some channels which enable private communication between specific participants. So it's not restricted. And pluggable consensus again supports algorithms like Raft and Kafka, and endorsement policies which define which members should approve the transactions. So why did we choose Hyperledger Fabric? Is because that it stands out as the ideal blockchain platform for enterprise use. So basically, it operates as a permission network, meaning that only verified participants can join, which makes it suitable for environments where trust and control are critical, such as the pharmaceutical supply chain, which we are using. And its real world adoption reflects its versatility. So, in supply chains, it's used by companies like Walmart to track food from farm to shelf. So in finance, it streamlines cross-border payments and it reduces fraud. In healthcare, it enables secure sharing of patient data. Governments also use it for digital identity and land registries. I think this is still a work under process, but it is used. And in manufacturing, it ensures parts and products are genuine. So that is why we chose Hyperledger Fabric for BioBit, because when trust, compliance, and data integrity, these all are non-negotiable. So the key Hyperledger components in BioBit include peer nodes, orderer nodes, certificate authorities, smart contracts, which is the chain code, and couch database. So the main job for the peer nodes is to validate and endorse the transactions and then eventually commit the blocks to the ledger. The orderer nodes maintain the consensus along the peer nodes and package transactions into blocks. Then the certificate authorities issues they issue digital certificates and enforce identity and access control. Smart contracts, which are also chain code, they define operations like drug creation and verification in a project. Couch database is used for maintaining the current state of all approved drugs, and it enables querying by certain parameters such as drug ID or batch number or so on. So here's how BioBit handles the life cycle of a drug using blockchain. So when a manufacturer submits the drug details, our backend triggers the create drug chain code function on the Hyperledger Fabric. So the peer nodes then validate this transaction to ensure that it meets the rules, and then the orderer node packages it into a block. Once confirmed, the couch database is a state database, so it is updated with the latest drug entry. On the other end, when a user scans a drug QR code, the system hashes the QR and compares it to the entries in the Fabric ledger. If there's a match, the system retrieves and displays the drug details. And if there's not a match, then it flags the item as potentially counterfeit and it alerts the user in real time. So this ensures that every drug can be verified on demand with complete traceability and zero tolerance for tampering. So these are some of the Hyperledger commands used in the blockchain part. So as you can see, the first one, this command initializes the fabric. It creates a channel and it starts the certificate authority. The second command deploys a chain code named as drug transfer. The third command, it invokes the drug creation transaction, and npm start launches the node.js gateway server, which has to interact with the Fabric APIs. So security through blockchain integration. So here security guarantees which are provided by Hyperledger are of utmost importance in our project. So data integrity is one of the most pressing issues in today's world, and transactions in Hyperledger cannot be altered once they're committed, which is a great feature of Hyperledger. Then auditability. Every step of the supply chain is basically logged. So there's no denying going further on. And yeah. Tamper resistance means that the QR hashes and drug records are immutable and no one can modify them. Fault tolerance, it uses Byzantine fault tolerant design, which ensures network resilience. So using all of these, end user trust is gained, and scanned drugs that don't exist in the fabric are flagged as potential counterfeits. And basically it empowers consumers with verification tools to verify if the medicine that they're taking is actually authentic or not. So Hyperledger uses role-based access control. So these are some of the roles and the privileges that we have assigned to each role. So the manufacturer has the privilege of registering drugs and sending them for approval to the RA, the regulatory authority. The regulatory authority can approve or reject the drugs, and they can access the audit logs. The end user can scan the QR code and verify the authenticity of the medicine. The gateway server has to interact via the APIs and handle log interactions. So the QR code verification and traceability. So how the QR code verification works exactly in a project from end user and manufacturer from end to end is that the manufacturer assigns a unique QR code to each drug, which is the first point in the system. And this QR data is then hashed and stored securely on the blockchain. The end user can then scan this QR code on their medicine via the front end, and the system hashes this scanned QR code and compares it with the ledger. So the ledger over here means the hash data for the QR code, which was added by the manufacturer. So if the match is found between these two hashes, it shows the full drug details. And if there is a mismatch, then the medicine is flagged as counterfeit and the user is notified for the same. The impact of this is that it is instant and it is reliable and it is directly linked to the immutable blockchain entry. So it is tamper-proof. So with BioBit, we've realized several key benefits that directly address the core issues of pharmaceutical supply chains. So first, we enable end-to-end transparency, ensuring every stakeholder from the manufacturer to the end user sees the same truth. Then our role-based access model builds trust by assigning clear responsibilities and permissions to each entity. So each drug unit is also immutably verified, and all records are stored in a tamper-proof registry. This is crucial for regulatory compliance and effective recall management. So, and after this, most importantly, we empower end users. Anyone in the end users can scan a QR code and instantly verify a drug's authenticity. There are no intermediaries or there's no guesswork. Ultimately, BioBit offers more than just a technical fix. It's like a decentralized AI ML powered system which is designed to eliminate counterfeit drugs and restore the trust in this whole system. So the front coming to the front end architecture and the role of front end in BioBit, it includes React.js, which is our core single page application framework, which enables you can say smooth transitions and dynamic rendering without reloading the page every time. Then React Router, which helps us with navigation and implements role-based routing so that manufacturers, regulators, and end users, these each of these can see only the interfaces which are relevant to them. Then for secure data transfer between the front end and the back end, we rely on Axios, which manages our API calls. Then we've also integrated JWT authentication. This allows us to handle sessions for each user type. So it ensures secure access and you can say persistent login states. Some of our key contributions include designing custom dashboards for each role, implementing a dynamic feedback system that shows whether a drug is verified or is it a counterfeit. And it also ensures that all user inputs are validated and securely transmitted via encrypted data pipelines. So overall, our front end acts as the user's trusted window into the blockchain. So the technical workflow, starting from the QR code to the blockchain, the full technical workflow. is that the user scans the QR code using our custom scanner component. This component is built using the React QR reader. This QR code data is then hashed on the front end using SHA-256, which is a secure algorithm. And then this hash value is then sent to the backend through an API call, where it is used to query the Hyperledger Fabric using the query drug function, using the drug ID. If the hash matches an entry on the blockchain, the React UI instantly displays the drug details, which confirms that it's authentic. And if there's no match, it immediately flags the drug as unverified or potentially counterfeit. And we've also implemented a perfect input validation and error and handling to manage the malformed or tampered QR codes. So this ensures that users can always receive clear and real-time feedback. Oh, so coming to secure form handling and the data flow in the application is for authentication and the form security, we are implementing the use of JWT tokens, which are handled at the front end level, and these are used for session persistence once the user logs in. We also use React Context API, which is used to manage the user roles and access across the app for different types of entities, as mentioned before. Control forms are present for the different entities like manufacturer drug entry and RA drug approvals and consumer drug verifications. And then we also implemented schema validation. So here the errors are validated before making an API call. And these errors may include missing fields or invalid dates. So coming to some pseudo codes in our project from the front end, blockchain, and full stack application part. So for the QR code handling, these are some of the pseudo codes. So it mentions that if the QR code is valid, then the hashed Q uses the SHA-256 algorithm to hash the QR code. And then this QR code is sent to the backend. Or if the QR code is invalid, it throws an exception. Then, for the blockchain verification result handling, if the backend response states that it's verified, so if the backend hashed value is matching with the manufacturer hash value, it displays that the medicine is authentic, or it just flags it as counterfeit. This is a pseudocode for form input submission. So if all the fields are valid while submitting the form, the Axios sends a post request using add drug API. And it also sends the JWT token for verification, or else it shows a validation error. So this is some of the logic implementation in the Hyperledger Fabric. So the summary of the methods. So the first method used here is add drug. So this takes inputs such as manufacturer ID, drug name, QR code data, etc. And it adds this drug to the ledger with a unique ID, which is based on the other parameters. Second one is we used here is query drug. So this one retrieves a drug's information by using its drug ID, and it throws an error if it's not found. Then delete drug is basically used for deleting a drug from the ledger by using the same drug ID and throws an error if it's not found. And error handling methods that we use in the Fabric, both query drug and delete drug methods, both of these check if the drug exists. And if it does not exist, it throws errors. And for data persistence, we've used put state and delete state to store and remove drug data on the ledger. So the backend architecture overview, some of the technology stacks that we've used. So for runtime, we've used Node.js. As we saw before, also Hyperledger Fabric implementation, we used npm start. So And then the framework we've used here is express.js, database, MongoDB, blockchain is Hyperledger Fabric, and for security, JWT tokens for user authentication. And for data flow, we've used RESTful APIs for the secure communication between front end and back end and the blockchain. So the back end of BioBit acts as the central coordinator between the user interface and the blockchain network. So the first responsibility of the backend is to handle QR code generation and validation, which ensures each drug unit is uniquely identifiable and securely linked to the blockchain records. Then it also functions as a middleware layer. It manages all the communication between the React frontend and Hyperledger Fabric. And this is through the secure use of RESTful APIs. Then beyond that, the backend is responsible for user registration, authentication, and role management. And by using this JWT-based access control, this basically enforces permissions for the different entities such as manufacturers, regulators, and end users. Then it also exposes secure APIs that allow us to read uh, from and write to the blockchain, whether it's adding a new drug or verifying one during a scan. Then finally, we've built in a strong input validation and error handling to prevent this malformed or malicious data from ever reaching to the blockchain layer. So here is a table displaying the different API endpoints between the backend and the blockchain. So the first endpoint is creating, which adds a new asset to the blockchain. Post method is used here to do the same. ID here refers to the drug ID, which retrieves the asset details from the fabric. Update ID updates the asset data on the blockchain ledger. History of the ID fetches the full history of an asset on the ledger. And verifying the QR code endpoint basically validates the asset using the QR code. So this was our